Alright, let's have a look at example 5. So for example 5, we're asked to write the results that we got on examples 3 and 4 for cosine and sine respectively, and represent this using sigma notation, so let's see if we can find a pattern of numbers here, and also so we can write the algebraic rule that represents this series right here. So well, let's start with writing the summation symbol, starting at n equals to 0 to, I'm going to write it as an infinite series because, well, of course it can generate infinitely many terms. And well, the most prominent feature here on both polynomials actually is that they are both alternating series. So let's start with an alternating factor. How about that? Negative 1 to the n. Would that work? Well, starting at 0, negative 1 to the 0 power should be positive, and sure, it checks. Alright, so we need something for the powers of x. Okay, what do we have? We have the invisible 1, 1, 3, 5, 7. Well, that's the sequence of odd numbers represented by 2n plus 1. And in the denominator, we also have this, well, this is technically an invisible 1 factorial. 1, 3, 5, 7, etc. factorial, the same 2n plus 1 factorial. Alright, so that's the series representation for sine in terms of sigma notation. Let's do the same for the cosine function. So first of all, let's start with sigma n equals 0 to infinity, negative 1 to the n, x to the, well, let's see if we can see a pattern. So technically, number one, right here, we have an invisible x to the 0, and in just the same way we have an invisible 1 factorial. Well, in order to keep the sequence 2, 4, 6, what would be the previous number? Well, how about 0 factorial? Alright, which is also 1. Both 0 factorial and 1 factorial are equal to 1. Alright, so in this case 0, 2, 4, 6, well, that's the sequence of even numbers. Let's to the n, 2n, and 2n, the whole thing factorial. Alright, and need to be careful when we say 2n factorial. We need to make sure that everything is inside of the parentheses, because 2n factorial is not the same as 2n factorial. Try it for some values of n, and you'll see how it's not the same. Alright, so let's look at example 6. Use a quadratic polynomial to approximate the value of the square root of 106. Alright, so what do we have here? They're not even telling us what function it is, but I think it shouldn't be like the most impossible task in the world to figure out what the function is. And in fact, this is something that you did in Calc 1. They gave you a number to approximate, and what you needed to do in some cases is to guess the function. But in this case, well, it seems like a good function, a good candidate for function is f of x equals the square root of x. Alright, and well, what's a good center to compute so we can approximate square root of 1.06? Well, on the one hand, we're going to use centered, we're going to do it centered at 1. So f of x equals square root of x equal, which is also x to the 1/2. This is, well, we're going to need the x to the 1/2 to take the derivative later, and evaluate f of 1, that's the square root of 1, which equals to 1. f prime of x equals to 1/2 x to the negative 1/2, which is 1/2 root of x, after cleaning up the negatives and rewriting this in radical form. This is f prime at 1 That's 1 over 2 root of 1, which equals 1/2. And then in this case, yes, that was great. We only need the quadratic polynomial, not the fifth one, not the 10th one. So just two derivatives, that's fine, not bad. So 1/2 times negative 1/2, that's negative 1/4. X to the negative 3/2. All right, equals negative 1 over 4x to the 3/2. And in this case, evaluating the second derivative at 1, we get negative 1 over 4 times 1 to the 3/2, which equals negative 1/4. So we have all the information that we need to find the second polynomial, or the second degree polynomial, p sub 2 of x, which is f of 0, no, that's not at 0, it's at 1 rather, right? F of 1 plus f prime of 1, x minus 1, plus f double prime at 1, x minus 1 squared over 2 factorial. So that's great. Nothing beyond the second derivative. This should be very short. So let's see. Okay, f of 1 equals to 1 from here. F prime of 1 equals to 1/2 from here. F double prime of 1 equals negative 1/4. So that's what we're going to plug in and simplify. So f of 1, which is 1, plus the derivative, which is 1/2 x minus 1, minus f double prime of at 1, that's negative 1/4 x minus 1 squared divided by 2 factorial. Let's simplify this, and this will be 1 plus 1/2 x minus 1 minus minus equals to plus. All right. Oh wait, no, that's a plus and that's a minus. That's 2 factorial, which is 2, times a 4th should be an 8. X minus 1 squared. And that's our second degree polynomial. And we're going to use this polynomial to find the value, to estimate or approximate the value of the square root of 1.06. That is, we're going to use this p sub 2 and evaluate it at 1.06. So that's going to be 1 plus 1/2, 1.06 minus 1 minus 1/8 times 1.06 minus 1 quantity squared. And this is approximately, well, first of all, let me highlight, so you can see where I plug in that value. And this should give us around 1.02955. All right. Now we're gonna come up with the same approximation, so we should get the same value. Well, maybe not the same value, or what, we'll see. So now centered at c equals to 0. Well, I know from here on it's gonna look like very tempting to use the same process, or rather the same function that we did before. All right, like, so the question is using f of x equals the square root of x. Think about it. Think about it if it's okay to use this function. So look at the work that we did before and see if there's any issues with it. Well, unfortunately, check the second derivative. The first derivative and the second derivative. Do you see how these two derivatives are not defined for x equals to 0? Well, then we have a problem. Then we need to come up with a different function instead. All right, so what are we going to do then? Well, so instead, so this, no, we're going to use a different function, a shifted function. Use f of x equals the square root of x plus 1. This way, when we take derivatives, it won't have any weirdness when we, well, in terms of having undefined values. So let's start. F of x equals the square root of x plus 1. Evaluating this at 0, 0 plus 1, that's the square root of 1, which is 1. Well, recall that this is x plus 1 to the 1/2, so we can take the derivative. F prime, that's 1/2 x plus 1 to the negative 1/2, and that's f prime of 0, 1/2 x 0 plus 1 to the negative 1/2 equals, okay, 0 plus 1, which is 1. That's going to be 1/2 1 to the negative 1/2, but well, 1 to any power will simply be 1, and then 1 times 1/2, that's 1/2. F double prime of x equals, okay, negative 1/2 times 1/2, that's negative 1/4, x minus x plus 1 to the negative 3/2. F double prime of 0 equals negative 1/4 x plus 1 to the negative 3/2, or rather not x, that's a 0 here. That's going to be negative 1/4 times 1 to the negative 3/2, which is also 1. That's going to give us negative 1/4. And well, in this case, do you see that the value that we're getting, they're pretty much the same? All right. So, well, so let's write down piece of 2 using, okay, f of 0 plus f prime of at 0 of f prime of 0 yeah, never mind. Yeah, f of 0 times x minus 0 to the first plus f double prime of 0 x minus 0 squared over 2 factorial. And well, piece of 2 of x, that's going to be 1 plus 1/2 x minus 0 and plus 1 plus negative 1/4 x minus 0 squared over 2 factorial. And do you see what's going on? We're gonna get actually the same approximation. 1/2 x plus, or rather minus, oh wait, no, rather minus 1/8 x squared. And then we can use this to do it in the calculator. So that's piece of 2. That's the second degree polynomial, the second degree approximation. And evaluating at 1.06, 1 plus 1/2 1.06 minus 1/8 1.06 squared. Well, the approximated value, okay, well, fortunately I don't have the result. I will have to do it in my calculator. Second quit. So that's 1 plus 1/2 times 1.06 and then minus 1/8 times, oh yes, 1.06 squared, 1.38955. All right, let's compare the results. Yes, different results. So we get different results when we find approximations at different centers, and we do different centers depending on the value that we want to evaluate this, right? So this concludes this section, and so I think it's a good place to quit.